All right. So last time we talked about the Karush-Kuhn-Tucker conditions, KKT points, if we will. So in certain conditions, if certain conditions not yet specified are met, then basically a linear combination of the gradients of the constraints and the gradient of the function needs to be zero in such a way that the linear combination of the equality constraints can be anything, and then the constraint for the inequality constraints, those need to be positive linear combinations, meaning that the gradients need to be multiplied with positive. So we combine these gradients and the sum needs to be zero. There are other constraints here, namely that either the coefficient for the gradient of the inequality constraint needs to be zero, or the inequality constraint itself needs to be active, meaning it's equal to zero, meaning it is limiting at that point. And obviously all conditions need to be met. So these are known as the KKT conditions, and points that satisfy these are the KKT points. Not all KKT points are optimums or minimums or something like this, not even local minimums. We will see examples of this happening, that they're not. Not all minimums are KKT points, but suppose that these constraints meet certain criteria, then the KKT points will be exactly the minimums. And we can say that the minimum, well, not exactly the minimum. The minimum, under certain conditions, the minimum will be found among the KKT points, and under other conditions, there will be only basically not one KKT point, but a set of KKT points which correspond to a similar minimum, meaning that the point has the same value, but there may be many such points. We took a look at some of these constraints. One of them was that if our functions are if our functions of the inequality constraints are convex and the equality constraints are linear. I say linear, it's actually affine, meaning there's a matrix AX equal, they're of the form AX equal B, these equality constraints. And if there is an interior point that actually satisfies these equality constraints, then the case is such that the theorem 5.2 tells us that the KKT point will contain one of those minimum. The minimum is found. Obviously, f itself needs to be continuously differentiable. The gradients at a given point need to be linearly independent for the active constraints and the equality constraints. If they're not, we'll see an example of a situation where they're not linearly independent shortly, and the minimum is found at the point which they are linearly dependent, and it's not a KKT point. So we'll see an example of that. So you have to make sure that if you are looking for, think about it in this way, that if you're looking for critical points, you can think of this KKT condition as a generalization of critical points of a function. If you have a continuously differentiable function, then a critical point can be found at the zero of the gradient. If it's piecewise continuously differentiable, then the derivative may exhibit discontinuities, points at which the derivative doesn't exist. Those are considered critical points as well. Like, take for example, the absolute value of x has a point at which the derivative is not defined, and it is the minimum of that function. So those are, in general, what we call the critical points. And this is a generalization of critical points, is that not only do we have to consider the critical points of the function, but we also need, and the KKT points, we also need to consider points that are such where the gradients of active constraints are linearly dependent because we'll see an example of that, that these will form these kind of sharp points in the feasible region at which we need to look carefully whether or not the function is well behaved, or whether the minimum might be found in such a point. Another theorem says that if we only have equality constraints, we can use the so-called Lagrange condition, and we'll look at the Lagrange condition shortly. If also we have a KKT point such that f and the cost function or the target function and the constraint functions for inequalities are convex, and the function equality constraints are of the form ax equal b, then our point, any KKT point, is a global minimum. That is an important thing to understand. So convex problems are very, very nice to solve in this case, because if you find a KKT point of a convex problem with, and the equality constraints there are of the form ax equal b, then the only thing we need to find is one KKT point, and that is a global minimum. That's a very powerful theorem here. So here was some example, which I'm now going to skip. We can transform this into this vector format and so forth. I'm not going to go into that now. Here was an example which we looked at. So there was a minimization problem of a third order polynomial. We have only inequality constraints, and we then transform these inequality constraints into the standard form, which we consider the standard format of when we look at the KKT points. And in those points, we get three different functions, G1, G2, and G3. So the constraints are of the form, all of these G functions are smaller than or equal to 0. And we can calculate the gradient, the Hessian. And we notice that this Hessian is positive definite in the feasible set because x1 is greater than or equal to 0. So we conclude that f is convex. Remember, the convexity of the function can be determined. I mean, it only matters if we are in the feasible region. If it's non-convex outside the feasible region, we don't care. Also, you can see that these constraints are linear. So given that these constraints are linear, in fact, the feasible set is also convex. So if we find a KKT point that is a KKT point, it will be a global minimum. And then different conditions are found, and we find one KKT point where mu1, mu2, and mu3 are all 0. So it's an interior point. And in the interior point, x1 is 2 over square root of 3, and x2 is 3 over 2. And in that point, the gradient is 0. So we actually know by now that this is going to be a minimum because it's convex. So this KKT point is a minimum. We just check the other conditions here, and none of them will actually yield a KKT point. If one of these would yield a KKT point, then we would actually have a situation where that point should have exactly the same value of the cost function as the KKT point we found at the interior. And because it's convex, in fact, any point on the adjoining line should also be a minimum point. But there are no other minimum points that can be found. So we conclude that yes, it has a unique minimum there, 2 over square root of 3 and 3 over 2. Not going to go into these details, but all these conditions led to contradictions with the assumption that the mu coefficients are positive. All right, so let's look at one example of when constraint qualifications are not met. So you see here is an example 5.9, and we find there is an equality constraint x to the 3 plus y to the 2 is 0. So this results in this kind of looks a bit like a parrot's beak, you know, this line here. And we are looking for the point that is closest to the point 1, 0. Technically, I mean the minimization of fxy, where fxy is x minus 1 squared plus y squared. And now if we formulate the KKT conditions here, we get the lambda coefficients, which are for the equality, so they can be positive or negative. And we can formulate it by calculating first the gradient of f, which stands at 2 times x minus 1, so that's 2x minus 2. 2 plus lambda, at 2y, that's in the gradient, and 3x squared, 2y, and then that vector times lambda is on the second part, you know, the gradient of h, and the sum of these should be 0. And if we look at this, we set this to 0. And we look at the second component, that comes out as 2 times y times lambda plus 1 is 0. So we must have either y is 0 or lambda is minus 1 for this to be satisfied. But if we set y to 0, it gives us x equals 0. And we get a contradiction because it doesn't actually satisfy this equation. The KKT condition is 5,4a is not met. 5,4b is met, but 5,4a is not met. The condition cannot be satisfied with y equals 0 and x equals 0. It does not satisfy that. And because it comes out at minus 2 equals 0. The other possibility is that lambda is minus 1, and if we take lambda is minus 1, then we get a point which is not a real number. So we don't get KKT point. There are no KKT points, but clearly if we look at this graphically, we know that the point 0, 0 is in fact a minimum of this. So what's going on in that point is that if we look at the gradient of f at that point, if we look at gradient of h, if we look at the gradient of the equality constraint function, x squared plus y squared, then the gradient of that constraint function comes out at 0. So we have an equality constraint that has a 0 gradient. The gradient vanishes. So while the curve incurred by x to the 3 plus y equals 0 is a continuous curve, the curve itself is not differentiable at 0, 0. I mean, the curve is continuous, but it's not differentiable. There is a point at which the left-hand side and the right-hand side derivatives are pointing in opposite directions. That's what happens here. So this one, the derivative goes to 0, and here the derivative goes to 0, but it's an opposite direction. So we have this sharp beak here at the origin. So, you know, if we look at this condition that was set here at theorem 5.4, the gradients need to be linearly independent. Well, there are no G conditions. There is only one H condition, and the gradient, there's only one gradient. But if we formulate the gradient here and we put it into one set, that's a 0 vector. So a set of vectors, if it contains the 0 vectors, even if it's just one vector, is not linearly independent, because the definition of a linearly independent set is that all linear combinations, non-trivial linear combinations, need to be non-zero. Well, if you have a 0 vector, then you cannot make a non-zero vector out of it by multiplying it with anything. So it's not linearly independent. So understand what example 5.9 says. It says that if you have a list of these equality constraints, think equality constraints for now. If you have a list of equality constraints and you get, let's say, a zero of the gradient of one of those equality constraints, then there is a risk that it forms a kind of a point which doesn't satisfy the KKT conditions because the gradient vanishes at that point, but it is a minimum. It is possible. So you have to check those points. Also, if you have inequality constraints and two inequality constraints meet at a point in such a way that their gradients are linearly dependent. So either they point in the different direction or they point in the same direction. So there is a situation where the borders of, you know, one constraint forms a border like this and another forms a border like this, and then they meet so that they're tangent to one another at some point. So that point may be, it is possible that at that point, there is a minimum, even though it's not a KKT point. That's a little bit hard to visualize, but yeah. So you have to make sure that you check the points at which the gradients are linearly dependent. Those points usually come out of these equations in such a way that the gradient equation doesn't have a solution, but you know, it has a solution that is contradictory. So you have to make sure whether look at those points. Yeah. Okay. Well, these are the warnings of those. Most of the examples that we look at won't have these problems, but you know, you want to be aware of that, these things happening. Okay, let's talk about equality constraints now then. Let's first assume that there are no inequality constraints. So the good thing about equality constraints is that we can now move to work on something called the Lagrangian. And that means that we can kind of take the KKT conditions and we can bake the whole thing into just one actual unconstrained problem at which we just have new parameters. You know, you see, what happens here is the original problem has a kind of a, with the equality constraint, there's a drop in dimension or degrees of freedom, if you will. So if you have three variable, let's say you have three variable problem and you introduce one equality constraint. That equality constraint induces a kind of a surface in the second, in the three-dimensional space. You know, some function must be equal to 0. So you're actually going to look for those points on a surface, right? So, but the problem here is that's a bit of a hard problem to solve. So if we formulate the KKT problem conditions, it actually gives rise to a problem that where we have this lambda coefficients, and we're going to be solving for the critical point of a function which has these x's and then these lambdas. So we're kind of not cheating, but you know, in a way, we're kind of we're baking this into the finding of the critical point, finding the gradients 0. We're baking it into a different problem, but which incidentally happens to be solved at a point where this KKT condition and the constraints are satisfied simultaneously. So the way we do this is we can let's formulate this in vector notation. In this case, the nabla f, the gradient of f is one vector, and then this h prime x is a matrix of the gradients of the different equality constraints. It's a matrix where we have the gradients of the different equality constraints. And then we formulate that into a matrix. We take the transpose and we multiply that with this lambda vector. And the lambda vector now, it means that we're multiplying each of the gradient with each these lambda. This is just a matrix notation of the fact that we're taking lambda 1 times the gradient of h1, lambda 2 times the gradient of h2, and so forth. So we have these two conditions, the hx vector, you know, where we have these different equality constraints, they must all be 0, as must the condition of the KKT condition be met. So how do we do this? Well, we formulate what is called the Lagrange function. And we say that this Lagrange function LZ now has a higher dimensionality. We have P constraints and N variables. So we introduce a new variable called Z, which has, the X, the point you are looking for, and lambda, the coefficients that go into the KKT conditions. And this is our new vector. Z, first there's the X part, and then there's the lambda part. We're just doing this in vector notation. We're basically solving these equations simultaneously. And we formulate what is called the Lagrangian as follows. We take the f of x plus lambda times h of t. H of x. So this may seem like it has very little sense, but we're kind of baking this into one big function where we have the cost function on one hand, and then we have lambda times the constraint on the other hand. This may be familiar from previous courses, this way of doing the Lagrangian. And now, if we take the gradient of this Lagrangian, this LZ, so it comes in two parts. The gradient, remember, they're the partial derivatives. The partial derivatives, if we take the partial derivatives with respect to the x part, then out comes the KKT condition, the gradient of f plus h prime of x times lambda. Because if we, I'm gonna just share I'm gonna share the whole screen so you'll see. So let me just draw. You're seeing what I'm drawing now. You see this equation here. Do you see my drawing? Is it visible?
No, it's not.
It's not. Okay. Seems it's not. Let me try. It's not yet visible. Okay, let me try it again. And let me just now try to draw. Is it now visible? No.
No.
Yeah, okay. I'm sorry. That's too bad. Okay, I can't help it now. It's for some reason it's not working. Okay. Well, if you look at the Lagrangian and you look at its derivative, look at the Lagrange function, the second, not the first two, but the third equation on page 120. So the Z function comes with two parameters, x and lambda, and f and h are the ones that depend on x. So if we take the derivative of this with respect to the x's, then we get the gradient of f plus then this lambda times the derivative of hx. On the other hand, if we take the derivative of this with respect to lambda, then the only thing that remains is h of x. And all of these need to be 0 for the KKT condition to be satisfied. So this only reduces to finding the critical point of this Lagrange function. And in fact, that's what we do. This can be done with, for instance, using Newton method or any other similar method. So it's actually not too hard to solve this with just the unconstrained optimization problem ideas. So you just transform the function into the Lagrangian, find the 0 of the gradient of the Lagrangian, and then move from there. There may be various zeros of the gradients of the Lagrangian, so you have to do the usual checkups that the Hessian is positive definite, Hessian of f is positive definite at that point, and so forth. But there are the same caveats that hold. But if you find a 0 of the gradient where of this Lagrangian, then that's a KKT point. again, there is the problem of local minima and so forth. So you have to make sure that you find the ones which you need. So, do all these double checks. But in any case, there is this returns the whole problem. It just kind of reduces the whole problem into unconstrained optimization problem, right? So to recap, if you have inequality constraints, you don't have to worry about anything, how to take into account these constraints. You just do the Lagrange function and minimize that. Well, not minimize, but find the zero of the gradient of that. Right. All right. Let's now have a short break. I'm going to stop the Zoom recording. So I asked you guys to look into this and consider what in this, if you are doing this Lagrangian transformation, and then you just start looking for the zero of the gradient of the Lagrangian, what in it guarantees that, or what's there to make sure that you get to a feasible point? Well, that's the part where you have the gradient with respect to lambda being zero, because if you take the derivative with respect to lambda, then it just reverts to h of x being equal to 0. Right. This can be done with Newton method fairly simply. So you calculate the different point you have different points, you have xk and lambda k, and then this search direction can be obtained by looking at the derivative of the towards the diminished direction of, or towards the 0 direction of h, and then towards the diminishing direction of the gradient part of that. So it will find you a point that, if you are choosing your method wisely, it will be a critical point where the 0 of the gradient is minimum. Not like it says here, there is a risk of converging to local minimum or a saddle point. So be mindful of that. Next order of business. There is this, I'm going to skip this part where we talk about the Hessian or the second order derivative and so forth. This is actually not needed. You can do the reduction without understanding how this works, but you can still, you can do this and go through this math. And I do really suggest that you go through here. The Hessian will have this specific kind of format here, because you have the second derivative with respect to lambda. It will be lambda, a second derivative with respect to lambda will always be 0, and then the cross derivative with respect to first lambda, and then x will be the h prime of x, and then obviously the second derivative with respect to x only will be the similar to the Hessian. It will have the component, upper right component of the Hessian, and then you have these Jacobians of h, right? So that's something that you can consider doing by hand, but it's actually not necessary, because if you just do the transformation, then you can calculate the gradient. I mean, any methods by which you calculate the gradients and the Hessians and so forth of this L function will be at your disposal. Okay. Here's some consideration of inverting block matrices like this, finding these so-called Schur complements and so forth. I'm not going to go there, but let's look at this example 5.11. So we're minimizing a function, which is a quadratic function. It's the second order polynomial. It's going to be convex. In fact, here, the second order polynomial, a minus x1 squared minus 4 times x1 x2 minus x2 squared, subject to x1 plus x2 squared equal 1. So we're looking for the minimum of this quadratic function as it stands on the unit circle. These are points on the unit circle. These, the unit circle, all those points are at exactly the distance 1. And if we can write this in matrix format, we can write this quadratic form into matrix format fairly easily. It's -1/2. I'm looking at this. Look at -1/2 times x transpose AX, where A is actually of the form 2, 4, 4, 2 matrix. And this h of x can be written as the norm of x squared minus 1, where x is the vector consisting of x1 and x2 is 0. And if we transform this into the Lagrangian format, first we formulate the KKT conditions. We can formulate the KKT conditions here as the gradient of f of x plus lambda times the gradient of h of x is equal to 0, h of x equal to 0, and we can rewrite this as minus ax, which is the gradient of fx, plus 2 lambda x is equal to 0. So we get this, and in fact, what comes out is a certain eigenvalue problem. So if you transform this a little bit, you take the matrix B, which is A over 2, so or 1/2 times A, that's lambda x. So we just formulate this as B of x is equal to 0. B of x is lambda x, and then the x squared norm squared is 1. So we find the eigenvalue of B and then the corresponding eigenvector, which has unit length. And here we have this cost functions. If we transform this into the Lagrange function and find it with the Newton method, we can do this in the exercises. Actually, I'll probably show you guys how to do this during the exercises, or maybe I'll show it to you at the end of this lecture as well. I mean, maybe, who knows? We'll do that if I have time. So points of interest from this equality constraints. The Lagrangian, you can approach the equality constraints in one of two ways. You can take and formulate the Lagrangian, after which you can just start working through that Lagrange functions gradient by any of the methods that we used in the unconstrained optimization part. This part of finding the inverse of this matrix, not that interesting. Or you can just do it by hand up to a point where you reduce it to another problem, like in here, which of course you can still solve it with the same method, the Lagrange method. We'll shortly do this. So what comes out here is that there are four different solutions to the method, to the KKT points. We will actually find 4 different KKT points of this problem, depending on where we start. And it will converge either to 1, -3, 1, or -3, with function value. These will be the points that are on the circle at this, like, I don't know, there's the figure which shows the geometry of the situation. So here are the contours, below are the contours of the cost function, and this red line here is the constraint function, and we found these 4 different points. In the middle of the picture, there is actually a minimum of the function, but remember that the function itself is it's convex, and it's nice that it's convex, but it doesn't help us here because the minimum of the function would be found at the origin. Obviously, setting x1 and x2 to 0 will lead the function to be 0, but it I was talking trash. Yeah, setting it to 0 actually doesn't seem to yield the minimum, in fact. Yes, obviously minus, I'm talking crap. Yeah. If these were pluses, then it would be this. Yeah. Sorry. Well, that's on record now that I in my mind I turned the minuses to pluses. So yeah. So what it says is those are actually maximum. That's actually maximum though. So because it's downward sloping. Yeah. It's got a maximum at the center and slopes downwards. So we're looking for the minimum on that circle. And then there are these 4 points. All of these are situationally, minimum or maximum. These ones are maximums. These are actually minimums. So when you start moving from here to here, you will increase, and here to here, you will, decrease. So these points near 1, -1, and -1, 1, these points are maximums, whereas this 1, 1, -1, -1, those directions, those points are the minimums we can see here. Yeah, sorry about that. At first I thought of it all wrong. Doesn't actually matter if it were the other way around, then the others would be just the minimums and the maximums. It's not of no consequence here whether it has a minus or plus. It's a different points. But all right. Any case, we'll look into that during the exercises and look at more examples of that next week. Inequality constraints here. Inequality constraints are different. You see that if equality constraints, we formulate the Lagrangian, we can just go on with the unconstrained optimization methods with a little bit higher dimensionality. And we find a zero of the gradient of the Lagrangian. We find a point that is a KKT point and satisfies the equality constraints at the same time. But with inequality constraints, this is not so easy. I mean, we could just look at equality, transform these different inequality constraints into equality constraints, and then just combinatorially check which ones of them when they are equal, and then formulate the KKT points and so forth. But that's actually not practical. There's no such nice methods for doing that. So we have to find other ways of baking this into an unconstrained optimization problem. So let's consider a problem where we are minimizing a function fx subject to some inequality constraints. So there are these so-called exterior penalty methods. So the idea of the exterior penalty method is as follows. We don't really want to care about, the thing is, we don't want to care about the inequality constraint as long as we are inside the region where they are all satisfied, right? Because, if you are at a point, remember we consider these are, given that these are not completely pathological functions, I mean, they're continuous, maybe continuously differentiable and so forth, they should give rise to a region where each gi of x is smaller than 0. Let's assume that we are at a point where none of them are binding, none of them are active constraints. Then we always have a little bit of room to maneuver. We can move in some direction from this point, and the value of the function changes a little bit. And if we find a 0 of the gradient somewhere, inside the region, then the constraints play no role in that. If you think about the KKT conditions, only the constraints enter the KKT conditions gradient equation that are binding, or that are active, where in that point, g of x is equal to 0. So if we are at any time, we are at a point where the constraint is not 0, it's negative, we should not consider it from the point of view of criticality or the point of view of the KKT condition at all. So if we are moving along the feasible region, then only those constraints matter that are at their limit. To take this into account, we take what is called an exterior penalty method, meaning that when we are at the limit, and we try to venture above the limit, go beyond, go into the infeasible region, then we start incurring a heavy penalty such that the cost function will increase so rapidly that you don't want to go outside. You want to get back up into that limit. So if we take a non-continuous function, which is 0 whenever we are not beyond the limit, and it's infinite, immediately we step outside the limit. Then this is a problem that it's not continuous. But if you think about this, let's minimize a function that has the original cost function plus then this p of gix, and add them all together. So as long as each of these gi of x is equal to 0 or smaller than 0, then we are only looking at the function f of x value. But as soon as any point goes outside the feasible region, then the cost becomes infinite. So clearly the optimum is found from the inside of the feasible region. Okay? The problem with this kind of so-called clever trick is obviously that this function is not continuous, definitely not differentiable. And if we are outside the region, there is no derivative or anything that can tell us where to go. We just know that we're outside. So if we take, let's say we take a gradient-based method, or Newton method or something, and we follow this g of x somewhere, this 5.7, this minimized f of x plus this penalty function x, and we follow it around and we step outside. We know where we came from into this outside, but other than that, we have no freaking idea where else to go except maybe go back to where we were before, but we don't have any idea where's the border. It's somewhere between where we were before and where we are now, but now it's infinite and there is no differentiability or anything here. So the only thing we knew that we jumped across the board. So we have to go back and try again. And this may be a method that doesn't actually give you a nice way of finding the actual minimum, especially if we have let's say we're using the gradient-based method and we take a pretty long jump. The line length is pretty long, and if we calculate it based on the gradient at that point in the interior, and we don't know when we hit the penalty and we go outside and we went outside, we have to back off until such a time as we find the border. So theoretically speaking, if we have a line search problem, let's say we decided the descent direction is that way, we move in that direction until we piece by piece, we look at it, we're going. Oh, hey, here's the border. So if we end up at the border, that's fine. There's no problem there. And if we're at the border, then we can start looking at other directions. Do they always point outside, or where, how do we do that? But this is not very practical because the functions, as they take into account the fact that we are outside, the penalty is not differentiable. And it's true, no matter what we do, even if we take, instead of taking infinite, we take a very large number, there's no differentiability at the border. So there is one way of doing this, is to define a penalty. Here's a quadratic penalty formulated like here. Obviously, if you take a quadratic penalty in this way, then you get this p of x. And now if you think about it, then this is gives a penalty based on how much you violate the condition. And in here, this basically it means that you take a quadratic penalty and you can then use that to back off in near the border. So when you are outside the border, you notice that, okay, my function is outside the border. We have a parameter, let's say r, that's how heavily the penalty goes. R is a penalty parameter here. And this is now differentiable. And the derivative of this will be derivative based on what the actual value of this violated constraint is and its derivative. So it will point us into the right direction if the penalty parameter is high enough to offset the the decrease in our cost function. So you see here, the cost function decreases. We're going, let's say we're going towards the border. The cost function decreases. Once we cross the border, the cost function may decrease, but the penalty coefficient will start increasing. So the increase in the penalty parameter, or the penalty factor here, the P of X, if you use this f of x plus r times p of x, it depends on what this r is. And if we choose this r large enough, then this will be differentiable, and it will drive us back towards the border. If we use, let's say, gradient-based methods. So in this case, what happens is we kind of go on gradient descent or Newton method or whatever that is, as long as we are at an interior point. And once we go outside, we start incurring a very big cost based on how much the constraints are violated, which then starts pushing the gradient or whatever method we are using back towards the border from the outside. And the higher this R factor here is, the penalty factor or the penalty parameter, the higher that is, the closer it will push us towards the border here. But the problem here is that now we're approaching this from the outside. So all the points are, technically speaking, infeasible. But let's see. Here's a template for doing this. First, we choose an R, which is, let's say, not too large, so that it doesn't jump impossibly high. We solve the problem with the penalty parameter. So we have f of x plus r times the penalty function. And we find a solution. If the penalty is sufficiently small, meaning we are just very, very near the border, we can stop and we have an approximation of the minimum. And if we are really, really meticulous about it, then we can just go and find a point from within that border that is close to this point or something like this. We have an approximate solution here that may be a little bit outside the region, but if we tolerate a little bit of error on the feasibility constraint, then we're good. We have an approximation of the minimum. If the penalty is high, but too high for our taste, but so that the cost function is still driving, the cost function decreases well into the infeasible region, and the decrease in this cost function dominates, and the penalty it pushes us too far away from the edge. Then we increase the penalty coefficient. We choose a higher one, like let's say we use a 10-fold increase in the penalty parameter, and solve it again. We should get somewhere near this point, but closer to the edge again. And we do this until we are satisfied that we are close enough to being feasible. So here's a theorem. The thing is, when you are minimizing the function, you should actually start the initial value from the previous minimum, because then, the only thing that is going on here will be, you're minimizing the penalty. You're minimizing the penalty and the cost at the same time. And you start there. So you are this close to the border. The next one will bring you closer, and next one bring you closer, and so forth, until you are close enough. Close enough. So here's a theorem about the penalty function. If we have a penalty function that satisfies the following conditions, the penalty function is non-negative. So whilst we are inside the region, it's 0 and we are outside the region is non-zero. And it's continuous. And if we assume that our cost function is continuous and our feasible region is closed, and at least one of these conditions holds, these are just such conditions that if we go too far away in any direction, the function will go to infinity, the cost function will increase to infinity. So that eventually the cost function itself will push us back. Or the feasible region is bounded. So there is no matter which direction we go to, the penalty will start kicking in. And a penalty goes to infinity when we go far enough. Then if we do this so that we are increasing the penalty factor or the penalty parameter to infinity, then the sequence we obtain by minimizing these successive problems will have an accumulation point, meaning that sequence will have a point that is the limit of this sequence. And well, it may have many accumulation points because it's possible that not limit of the sequence, because accumulation points are different. It may oscillate between different points of the problem. And but every accumulation point, if it has a limit, you can think of it this way: if it has a limit, then the limit is a minimum, and also that if it's a limit, it's an accumulation point. If it has several limits and finite limits and accumulation points, then every accumulation point is a minimum of that. So I think it's best to think of it this way, that it has a limit. I think, strictly speaking, the theorem doesn't guarantee that, but I think it would be best to think of it this way. So that the penalty of these points goes to zero, and the optimums of these different successive optimization problems will converge to a point that is a global minimum of the constraint problem. And this is a very convoluted way of saying the external penalty method works, right? That's a very convoluted way of saying it, but it actually, this theorem just states that as long as either the function goes to infinity if the problem is not bounded, if the feasible region is not bounded, or if the feasible region is bounded and the penalty goes to infinity, then this method works in determining the optimum of the problem. The thing about this quadratic penalty function is that it's continuously differentiable, but its second derivative is discontinuous at zero. And this means that this penalty function has a discontinuous second derivative. So its Newton method is not really an option to that. So, and otherwise also straightforward use of penalty methods is somewhat of a problem in this for this reason. I mean, no matter how you try to get about it, if you define this penalty function in such a way that it's zero on the inside, and then at that zero it starts increasing, then at least some higher order derivative of it will be discontinuous at that point. This is basic analysis. It's impossible to generate well, I'm not saying it's impossible. There is no easy way. Let's say there is no easy way to have a function that behaves nicely so that it's zero on the inside, and then at the border starts increasing rapidly enough to work as a boundary. function. So that's a weakness of the exterior penalty method, but it does work. Theoretically speaking, it's not what it's just that it's not easy to use all those methods. So for instance, using the quadratic function, if you take the first derivative of x squared, that's 2x, that's still fine. That's continuous. So it's 0 here, and then, but the second derivative already, I mean, it's got second derivative, which is always 2. And, you know, after the, at this there's a discontinuity of the second derivative at x equals 0. So the external penalty method is not always very very good in this way. I mean, it does have certain problems regarding Newton's method, for instance. So as long as you are outside the feasible region, the Newton method, for instance, barring any other problems, should work. But when you are at that point, when you have a risk of crossing that point, crossing the boundary to the inside, there is an abrupt change in the second derivative. So that's not, it makes it a little bit unreliable when the steps go towards the inside of the region, or cross the boundary of the inside and outside of the region. So there's a problem there. So here's an example. Let's take a quick look at that. So we have a quadratic function here, x1 squared plus x2 squared. Basically, we're looking at the distance from the origin, subject to x1 times x2 greater than or equal to 0. So we have this hyperbola here, and we're looking at minimizing the distance from the origin. Is there a picture here? There's no picture drawn here. Okay, let me draw a picture for you. Not everyone needs a picture, but let me draw a picture of what's going on here. So we have here a coordinate system. This is just paraphrasing it. So this is supposed to be x1 times x2 is greater than or equal to 1, and this. So I'm going to draw this shaded region here. So the feasible region consists of this and this part of the quadrant, and everything else is infeasible. x1 times x squared must be greater than or equal to 1. So anywhere here or anywhere there is fine, and we're looking to minimize the distance of square distance from the origin. So here, if you use a quadratic penalty function, the p of x will simply be p of x will be simply x squared. And if you take p of g of x is 1 minus x1 times x2. And you get this minimized function. And now it's got r and it's got x1 and x2. This example is done symbolically, meaning that, or in a closed form, so that it means that we're minimizing this in general with respect to r, not for a particular value of r. So if we calculate the gradient and set it to 0, then given that if we're inside the region, we get the 0 of the gradient at 0, which is not surprising. So if we disregard the penalty, then we would get the origin. But that is infeasible, right? So at this infeasible point, we must look at this, what's going on, and we must set r to something positive, and we assume that x1 and x2 are not 0, and 1 minus x1 x2 is greater than 0, so that we are incurring a penalty. So we get this gradient with respect to x with the parameter r. We get these two equations. We find that the penalty is x1 over r times x2, or you know the thing that goes into the penalty function, the violation of the constraint. And substitute this into the second equation, we get that x1 and x2 needs to be plus or minus x1. So we will find the minimum at a point where x1 is either x2 or minus x2. If we set x1 and x2 to be the same, and look at the first equation in the gradient equation, we get that x1 approaches, well, x1 as a function of r will be the square root of 1 minus 1 over r, plus or minus. Now, as r goes to infinity, then x1 will then approach 1 or minus 1. So we basically get 2 points. We get 1, 1, and minus 1, minus 1, which as limits as r goes to 0. So, or sorry, infinity. So it would be roughly those 2 points there, which is obviously what is going on. Right. Another possibility of that is to come up with a penalty method by adding a slack to this g of x, saying that g of x plus some ui squared is 0. And we can then transform it into a free problem. I'm going to skip. Well, there's an example here, the same problem as before in the example, we're solving it. Not going to go into details. You can verify this example. I'm not going to use too much time on that. So it reduces pretty much the same way, only this time we have this third equation, because these are all equalities. We can transform this into Lagrangian, kind of like. So we have this x and u. So this u is now the slack variable, but we have to that minimize with respect to that slack variable u also. And then we get the same equality, same inequality equation from the penalty, or the same equality equation from the penalty, with the gradient as we did before, and we can solve it just like before. We can apply also for the inequality constraint the problem when we have f of x subject to, the equality constraint. So if we have a subject to equality constraints, h of x needs to be exactly 0. We can minimize the square of h of x, because as long as h of x is non-zero, then the square of h of x is positive. So if we're minimizing that, then we can use that as well. We'll see examples of this in the exercises. We'll do this a couple of times. So here are other examples, like we're finding a point on the line x plus y is equal to 1. So that's the line that doesn't actually go through the origin. It goes through 0, 1, and 1, 0, and it's a downward sloping like this. So we're looking for the point on that line that is closest to the origin. So that way we can find minimize x squared plus y squared subject to x plus y minus 1 is 0. So we penalize this by taking x plus y minus 1 squared and multiply that by r. And then we get some kind of equation where as r goes to infinity, it approaches the point 1/2, 1/2, which is closest to the origin. So this is just an algebraic example, but in fact, you can do this to almost any function that you like and add these penalties. So one way to use this external penalty method is to just take into account all the constraints and then just take the violations of these constraints as penalties and then just drive where it takes you. That's not necessarily very efficient or very effective because of the phenomenon that especially with the inequality constraints at the region's border, you get discontinuities of the second derivative. I'm not going to talk about the augmented Lagrangian method at this point. So instead, I'm going to go through this example here and do this with MATLAB, this example with the Lagrange method, just to show you what's going on. I'm going to stop this share. I'm going to pause this recording for a little while. I'll give you guys a little break now. Resume the recording. Sorry. Yeah, so now we're live. So I've transformed this same example. So here I calculate, this is my function. This is the constraint function. I calculate the Lagrangian. Now it's got, I need to take here LS. That's my Lagrangian. And my Hessian, and then I need to calculate the L function, but it's got 3 parameters, and the Hessian right there. If I want to calculate it, I'm not going to calculate the plot surface because I'm doing this. So start with the gradient method. So we can start from, and probably not.
I think you also need to change a little bit before the functions, those FM.
Oh yeah, this one. Yeah,
yes, those.
Yeah. Sorry. Yeah, I was just taking the template. So I'm having these functions. So I'm now at my liberty to use this. I have to put the third parameter here and calculate this. I'm not going to draw any draw line and so forth. So I probably want to use the Newton method here. So I'm wanting to calculate the this needs to be the gradient of L, and this needs to be the Hessian of L. And I'm not calculating this. Instead, I'm calculating this with the HK, and this should be GL, and then this HK should be HL. I'm calculating the norm and the point, and at the end, I'm going to calculate this LXK. So I'm just going to try this now directly with that should be the Newton method. So I'm going to have to evaluate this part. Sorry. I'm not going to. Yeah. All right. So I have here the Hessian. You see the Hessian has a 0 at there. That's a one sanity check that needs to be the case. And then I'm going to just run this through. I have no idea whether this will work. I haven't tried it. Matrix was singular. Okay, there's a problem there. Yeah, there's a problem. I don't want to calculate that as well. I want to calculate this. Yeah. Okay, this was printing the TK, so I'm just gonna print here 1. Okay, let's try it again. I mean, the matrix was singular at that point, so let's try some other point. Yeah, it was gonna be singular because I was actually calculating it at the origin. Huh? What? Why is it not evaluating this? Okay, it didn't work. Okay, I have to double check. I'll do this in the exercises. There's something that I need to do a little bit differently here. So you see, these are ridiculous numbers here. So yeah, I probably did something really weird here. Maybe I made a mistake here somewhere. I'll have to double check. I'll have to double check. I'll do this better. I mean, I have a all proper there. I just trying to wing it now. So yeah, I'll have to try and see if I made some blunder there. So I'll do it properly for you so that I'll show you in the exercise. Okay. Sorry, I have to cut this short.